Okay, so to wrap up chapter 5, this is the last section on page 19. Okay, interpolation, extrapolation. Example 1 right here. Jenna borrows money from her parents for a school trip. She repays the loan by making regular weekly payments. The graph shows how the money is repaid over time. The data are discrete because payments are made every week. Okay, so remember last week we talked about discrete and continuous. So discrete meaning that you don't have decimal values in between. So like for example, since she's repaying every week, she's not paying like after a day, after 5 days she pays 50 cents or something like that. So that's why the data is discrete. She's not paying in between the weeks. How much money did Jenna originally borrow? So looking at this graph right here, how much did she borrow originally? Claire? $200, right here. Your initial value, what you start off with. So she borrowed $200 for this trip, right? How much money does she owe after 3 weeks? So if you take a look at your axis right here, this is the number of weeks and this is the money owed. So at 3 weeks, which is right here, this is 3 right here. So if you go up to your graph, right, you reach this point, okay? And then if you go across to your y-axis, it tells you exactly how much she still owe after 3 weeks. So how much does she owe after 3 weeks? Vincent? 140, right? Because you can see by the scale, it's between 120 and 160. So each of the boxes are $20. So 140. How many weeks will it take Jenna to repay half of the money she borrowed? So if she borrowed 200, half of it means at 100. So at 100, which is right here, this is $100. So if you, again, draw that dotted line over to where your graph is, and then come down, okay, how many weeks will it take her? Yep, 5 weeks, between 4 and 6 right here. So it's 5 what? 5 weeks. Okay? Showing the units will tell me if you understand the problem or not. So if you right here, you said, how many weeks will it take Jenna to repay? And you said $5, tells me that you don't really understand the question. Okay. How long until she repays the whole thing? So when will she repay the whole debt? Let's see. Looking at this, Sayan? 10 weeks, right? Right here. This last part right here. Okay. 10 weeks. And then the last question is, how much did she repay every week then? Derek? Every week, each week. Jason? $20 per week. That's right. 20 per week. Okay. Two different ways on how you can calculate that. One, you borrow 200 and then you took 10 weeks to pay it all off. So 200 divided by 10, that means it's $20 per week. The other thing you could have done is looking at this. Every box is 1 week. Every box is 1 week. So how much are you going down by every time? You're going down by $20 every time. Okay. So good. Okay. So this is an example of interpolation. So notice the title of this is interpolation, extrapolation. Interpolation is using data within our graph. Okay, that's what interpolation means. Maybe. Okay. Example 2. Maya jogs on a running track. This graph shows how far she jogged in 10 minutes. Assume Maya continues to jog at the same average speed. use the graph, predict how long it will take Maya to jog 2,000 meters. Okay, so looking at this graph right here in example 2, what's the problem? My problem right here is that it only goes up to 1,200 meters. So if I want to figure out 2,000 meters, what do I have to do? I have to extend my graph. So 1,000, 1,200, the next one 1,400, 1,600, 1,800, 2,000. Okay, remember you have to go in the same scale as the rest of the axis. Same thing right here. So every box is a minute, so then this is 12 minute, 14 minute, 14, 16, 18, 20. Okay, so what do you think I should do? How do I predict for 2,000 meters? What do I have to do with this graph? Vincent? I can use the line, but my line only goes up to here, so what can I do? Increase it, extend it, right? Why can I extend it? Because it says she's continuing at the same average speed. So I'm gonna extend my line like this. Okay. And based on that, based on the extension, 2,000, going over to my graph, coming down, roughly how long is it going to take her to run 2,000 meters? Yep. 17 minutes right here. Good. Okay. And predict how far Maya will jog in 14 minutes. So at 14 minutes, I'm going to go up to my graph again, my extended line, and then go across. On the assignment tomorrow, if you're off by a little bit, it's fine. I'm just gonna, like, let's say if you said something like 1,000, obviously that's wrong. But if you say it like something about like 1,600 or 1,800, that's fine as well. So here, after 14 minutes, it looks like Maya's gonna have ran 1,700 meters. Okay. And in order to answer these two questions, what assumption did I have to make? I actually kind of said it earlier. Yep. Right. She's going at the same speed. Because otherwise I can't extend the line. By the way, a quick little question here. What if she took a break? What would happen to this line right here if she took a break? So let's say she got really tired after jogging that 2,000 meters and she needed a 10-minute water break. Derek?
Maybe flat for 10 minutes.
Flat. Like, what do you mean by flat?
Not going down or up.
Not going down or up, right? So it's going to be a horizontal line to show that time still goes on, but she's not gaining any distance. So it's going to be a horizontal line if she takes a break. Okay. Is this a discrete or continuous graph? Okay, who says discrete? Who says continuous? Good. Okay, because from the 1 minute to the 10-minute mark, she doesn't teleport, right? Every minute, especially every time that you have time as your independent, it's almost always continuous because the minute keeps going. Okay. Okay, last one right here. Oh, sorry. So this interpolation, where our data is within the data, and then this is extrapolation, extra, because we have to extend it. Okay, last example. So use this graph of a linear relation, determine the value of x when y is 3. So can you guys do this one? Okay, so when y is 3, what's your x value? And then when x is 5, what is your value? Okay, take 30 seconds, try this one. So first thing you want to do, extend that line. So when y is 3, okay, so when y is 3, which is right here, I'm looking at this point. Okay. Shakai, what's my x value right here at this point? Okay, so when y is 3, which means right here, I go over to my extended line and then I go down. The x value is -5. Excellent. Since I had to extend the line, Danny, is this interpolation or extrapolation? Since I had to extend the line. Is it inter or extra? Extra. That's right. Extrapolation. See the word inside extrapolation? Extra. Because you had to extend it out. Okay. And let's see. Emmy, when x is 5. So when x is 5, which is this point right here. Okay, going over to my y-axis. What's my y-axis? What's my y value there? So this value right here. Okay, for my y, every box is 1. So when x is 5, I'm going to go up to my graph and then go across to my y. So this value right here is... Okay, so each one is 1. So 1, 2, 3, 4, 5, 6. So the next one. Hannah, can you help? This value here? 7, right? Okay. And Alex, is this an example of interpolation or extrapolation? Did I have to extend my line to get this data? So it's inter, right? That's inter. Okay, so extrapolation, interpolation. Question? Oh, true. It could be around 6 because right here you can see when it's at 6 minutes, it's actually 7. Yeah, so I would say it's more like 6.6. But as I said, like tomorrow when you do the assignment, if you're just off by a little, it's okay as well. Okay, so nice and easy lesson, 14 minutes. So for the rest of the class, please work on page 20, 21, and 22 to wrap up this chapter.